Assalamualaikum, and today I am going to present about our assignment project. My name is Asma binti Rosli with metric number B0821101130, and these are my group members. For introduction, the demand for reliable RF systems in telecommunications is rapidly growing. Central to these systems are microwave passive filters, which ensure signal integrity by allowing only desired frequencies to pass while blocking unwanted signals. Microwave passive filters are designed to manage frequencies effectively. They are created using the insertion loss method, which minimizes the loss of signal strength as it passes through the filter. The insertion loss ensures frequency selectivity without significantly degrading the signal quality. Transmission lines maintain signal integrity from the source to the destination. Evaluating transmission line circuits involves analyzing parameters such as impedance matching, signal reflections, and propagation characteristics. Next, I will be discussing two key aspects of RF systems, which is the design of microwave passive filters using insertion loss method and the evaluation of transmission line circuits. Microwave passive filters, as they allow desired frequencies to pass while attenuating unwanted signals, ensuring signal integrity. The insertion loss method focuses on minimizing signal power loss as it passes through the filter. The design process involves several steps like define filter specification like passband, stopband, and allowable ripple. Next, choose an approximation functions. Synthesize a low-pass prototype using inductors, capacitors, or transmission lines. Next, transform the prototype to the desired frequency range. The synthesized filter is then implemented using structures like microstrips or waveguides, ensuring minimal signal degradation and optimal performance. In RF systems, impedance matching minimizes signal reflection and maximizes power transfer by matching the characteristic impedance of the transmission line with the source and load. As parameters describe the behavior of RF networks, providing insights into return loss, insertion loss, and isolation. Signal reflection occurs when impedance mismatches, causing interference. The voltage standing wave ratio, or VSWR, measures the quality of impedance matching. Propagation characteristics like phase velocity and attenuation constant determine how signals travel through the transmission line. These are influenced by the line's physical properties. In multi-line systems, crosstalk and interference can degrade signal quality. It's important to evaluate isolation between adjacent lines and design strategies to mitigate these issues.
Assalamualaikum, my name is Hajarul Elia binti Nazarin and I am going to present about low pass filter. For low pass filter, we choose 3 GHz cut-off frequency, insertion loss of 32 dB and 6 GHz, 0.5 dB equal ripple, and first we need to find omega versus omega C minus 1. To find omega, the formula is 2 pi f, and to find omega c is 2 pi fc. And we get 1 for the normalized frequency. Next, we need to find the value of n at attenuation versus normalized frequency table. So, using the value of insertion loss and the normalized frequency that we acquired, we get n equals to 5. After we get n equals to 5, we need to observe the 0.5 dB ripple table at n equals to 5. So we have G1, G2, G3, G4, and G5. Next, we need to calculate the value of a capacitor and inductor. We use Rs equals to 50 ohm, and we find capacitor 1 with using the value of G1, and we calculate L2 using the value of G2, and we calculate C3 using the value of G3, and in L4 using the value of G4, and C5 using the value of G5. This is the circuit that we constructed. because we have G1 to G5. Then we have three capacitors and two inductors with uh, the term we use 50 ohm, and using the value of uh, capacitor and inductor that we have calculated. This is the result that we obtained after we simulated the circuit. We can see that the cutoff frequency, it attenuates at 3 gigahertz, and by observing at negative 32 dB, we get 5 gigahertz. This is the Richards transformation after we constructed our circuit. For capacitor, we transform it to open circuit, and for inductor, we transform it to short circuit. For the capacitor, we need to use the formula 1 over G from the 0.5 dB ripple table.
Okay, this is a Kuroda identity. So for this Kuroda identity, we use case one, which is a shunt step, followed by TL, which is or transmission line. So Z1 is the transmission line, and Z2 is the shunt step that we use from the Richard transformation. And after we do this calculation, and we need to draw it in a series. So from the shunt step open circuit, and then we get it into a series circuit. Okay, so next we need to form the Richards transformation from the Kuroda identities. So as you can see here, this is the formula from the Kuroda identities, and we need to transform it to the Richards transformation. So on this part, so we already changed it from the shunt tap open circuit into a series circuit. Okay. Okay, for normalized impedance for different stub and denormalized for 50 ohm impedance. First, the normalized impedance for different stub, we get this value from the previous calculation, and then after we get the value, and then we need to implement it on the impedance. So this is the final result that we get. And after after that, denormalize with 50 impedance, 50 ohm impedance. So for 50 ohm impedance, we only need to times by 50 to get the denormalize with 50 impedance. Okay, so after we done with the normalize and denormalize, then we need to construct the microstrip fabrication of final filter. So this is our final microstrip fabrication of the filter. So as we can see here, it start with the 50 ohm and end with the 50 ohm also. This value is we get from the previous uh, denormalized impedance. Okay, next, we construct a low pass filter with MSUB. So for the MSUB, the specification already given in the report. And then for this low pass filter, we use 6M LIN and 5M LOC and 5M TEE. So for the value for MLIN, we take the value from microstrip fabrication on the upper part, and for the MLOC, we take the microstrip fabrication value from the lower part. So for the MTEE value, we take from the MLIN 1 on the left side, and on for W2, MLIN 2 on the right side, and W3 for from MLOC from the bottom part. Okay, so this process is repeat for another MLIN, MLOC, and MTE. Okay, so this is the result for the low pass filter before tuning. So this is our layout that we get, and this is our table dB versus frequency. So for the M marker one, we get 3 gigahertz at 0.429 dB, and for Marker 2 we get 6 gigahertz at 25 dB. Okay, this is the after tuning result. So this is the layout after tune. After we tune, this is the layout result that we get, and also this is the graph low pass filter that we get after tuning. So for the marker one, we get the 3 gigahertz and at 0.823 dB, and for marker two, we get 6 gigahertz at negative for 41.779 dB.
Assalamualaikum. My name is Nur Inshira Izzati. My matrix number is B0821100056. Today I will explain about bandpass filter design. This is the calculation. So we get the question is 3 gigahertz center frequency FO, 350 megahertz is our bandwidth, 0.5 dB equal ripple, and n equals to 4. So first, we must calculate our lower cutoff frequency F1 equals to 2.825 gigahertz. Our upper cutoff frequency F2 equals to 3.175 gigahertz. So then we must calculate the WO. 2 pi FO equals to 18.85 gigahertz. W1 equals to 17.75 gigahertz. W2 equals to 19.95 gigahertz. Then we calculate this, we got 0.12. Then this is the equation for bandpass. L1 and C1 is the series. Same goes to the L3 and C3, while L2, C2, L4 and C4 is the parallel. So as we can see in the table 0.5 dB ripple, we use the n equals to 4 from G1 until G4. Okay, now I will explain about the schematic that we design in the ADS. So as we can see, the first one is the series, then the parallel, series and the parallel. So according to this graph, we get the bandpass filter. For the FO, we got 3 gigahertz. For the F1, we got 2.89 gigahertz. For the F3, we got 3.176. So it's related to the calculations that we got. The next slide is discussion. Low pass filter design. Design a low pass filter with a cutoff frequency of 3 GHz. Ensure the filter has an attenuation of 32 dB at 6 GHz. Incorporate at 0.5 dB equal ripple characteristic in the pass band. While for the band pass filter design a lump band pass filter with a center frequency of 3 GHz and a bandwidth of 350 MHz. Implement a 0.5 dB equal ripple in the pass band and ensure the filter order n is equal to 4. Implementation considerations. The practical aspects of implementing these filters, including component selection and layout, address potential challenges in achieving the specified performance parameters. Consider the impact of real-world factors such as components, tolerance, and parasitic elements on filter performance. In conclusion, designing and implementing filters for specific frequency requirements, a low-pass filter is achieved with a 3 GHz cut-off frequency, ensuring 32 dB attenuation at 6 GHz with a 0.5 dB equal ripple. Similarly, for a band-pass filter with a center frequency of 3 GHz, a bandwidth of 350 MHz, a 0.5 dB equal ripple, and order n equals to 4. A lumped element design is employed to meet these specifications. These design choices ensure precise frequency control and desired signal attenuation for optimal performance in the given applications. Thank you.